Hey there, organickers! In this video, I want to talk to you a little bit about factors that influence acidity, or factors that make an acid a strong or a weak acid. You may be presented with an acid-base reaction like the one that you're looking at here, and I might ask you, on which side of the arrows does the equilibrium lie, to the right or to the left? Or I may ask you to compare acid strength or base strength. You already know that one thing you can do is go to your pKa table and look up the pKa of the two acids I'm asking you to compare. Well, one or more of those pKa's may not be in your pKa table, and you're going to have a look at the structure of the acid or the conjugate bases in order to decide which of the acids is the stronger of the two. And remember that your equilibrium will always lie on the side of the weaker acid and the weaker base. So the first thing that you have to do is identify the acids and the bases in any acid-base reaction. You're going to have an acid and a base on the right and an acid and a base on the left. Water, you may recall, is amphoteric, and it can act as both acid and base. You need to figure out who's giving up the protons. So on the left side of our reaction, this species is our acid, and HA is not a real acid, it's just a generic representation for any acid. When HA gives up a proton, it forms the conjugate base A-. So on the right side, H3O+ must be our acid, and the conjugate base is H2O. I could also just call water the base, and I could say that H3O+ is the conjugate acid. Once you've identified the acids and the bases on either side of the arrow, you need to have a look at the bases and decide which of those bases is the most stable. So the factors that increase the stability of the conjugate base, the more stable the conjugate base, the stronger the acid will be. There are four factors that influence the strength of any acid, and they are the size, electronegativity, inductive effects, and resonance. And since these four factors are important and I want you to remember them, I'm going to say that again. The four factors are size, electronegativity, inductive effects, and resonance. In this video, we're going to cover size and electronegativity. In part 2, we'll talk about resonance and inductive effects. So what am I talking about when I say size and electronegativity? Electronegativity of what? Well, what we're talking about is the atom that bears the negative charge, or the unshared pair of electrons, in the conjugate base. So as the size of this atom increases, the acidity of the conjugate acid will also increase. As the electronegativity increases, acidity, again, will increase as well. So that's pretty straightforward. However, what is confusing is that size and electronegativity are opposing periodic trends. As the size of an atom increases, its electronegativity decreases. As the size of an atom decreases, its electronegativity increases. So you have to decide which of those two factors is predominant. So let's go back and review these periodic trends that you should have learned in your general chemistry course. And we really only need to look at the right-hand side of the periodic table. Remember that we organic chemists are not all that adventurous, and we pretty much stick to the upper right corner of the periodic table. And let's blow it up and have a closer look. And let's first look within a period. You may recall that electronegativity increases in this direction, and size increases in the opposite direction. So from left to right, size decreases. And if I consider the four atoms from carbon to fluorine and look at their atomic radii, carbon has an atomic radii of 185 picometers and fluorine 135 picometers. So this represents a decrease of 27% across those four atoms. Remember that from left to right, our electronegativity increases. And if I consider those same four atoms, carbon to fluorine, Carbon has an electronegativity of 2.5. Fluorine has an electronegativity of 4. This represents an increase in electronegativity of 60% across those 4 atoms. So you have a larger increase in electronegativity as you go from carbon to fluorine. So within a period, electronegativity is the predominant effect. Let's consider what happens within a family. From the top to the bottom, that our size increases, but from top to bottom, our electronegativity also decreases. So going from fluorine to iodine, we go from 135 picometers to 215 picometers. That's an increase of 60%. From top to bottom, electronegativity decreases. And from fluorine to iodine, we go from electronegativity of 4 to 2.5, a decrease of 37%. So we have a larger increase in size than we have a decrease in electronegativity. This tells us that within a family, size is the predominant effect. Let's look at a couple of examples. Let's look at this acid-base reaction here. We have hydroxide anion reacting with hydrofluoric acid to give us water, an F-. Remember that our hydroxide anion and our fluoride anion have to have a counterion. That could be sodium, lithium, potassium. I'm just not showing it because it's really acting just as a spectator ion. It's not participating in the reaction at all. So the first thing we need to do, remember, is identify our bases. Those are usually going to be the species with the negative charges. So we have an OH-. Remember what that really represents. We have an oxygen here, which bears the negative charge. We're going to compare that to a fluorine on the right side of the reaction that bears the negative charge. Remember that within a period, the predominant effect is electronegativity. Fluorine is more electronegative than oxygen. This means that fluorine is more willing to bear the negative charge, or in other words, HF, hydrogen fluoride, is the stronger of the two acids. So my equilibrium is going to lie to the right. And if I compare the pKa's of my two acids, HF has a pKa of 3.2, whereas water has a pKa of 16. Remember that I'm always going to go towards the side of the weaker acid and the weaker base, and the weaker acid will always have the larger pKa. So we observe this trend as we move across the second row of the periodic table from carbon to fluorine. What we're talking about is each of these atoms giving up the proton that is shown in red. So a carbon acid will be the weakest acid, whereas HF would be the strongest acid. And if we consider our pKa's, we see that our pKa's do fit this predicted trend, with the pKa of methane being around 50. And I say around 50 because these carbon acids are such weak acids that we really can't measure their pKa's very accurately. And our pKa of hydrogen fluoride, all the way to the right, is 3, so it's the lowest. So again, as electronegativity of the atom that bears the negative charge in the conjugate base increases, the acidity of the conjugate acid also increases. Let's consider what happens within a family. Here I'm showing you another acid-base reaction, and the first thing we need to do is identify the acids and the bases. Our two conjugate bases are SH- and OH-. So we have the negative charge on a sulfur versus a negative charge on an oxygen. If we go to our periodic table, we can see that oxygen and sulfur are within the same family, with sulfur being below oxygen. So sulfur will be larger than oxygen. And remember that within a family, size is the predominant effect. This means that SH- will be more stable than OH-, so our stronger acid is H2S. The equilibrium for this reaction will lie towards the left. Remember that we always lie towards the side of the weaker acid and the weaker base. And if we look at our pKa values, we can see that water has a pKa of 16, hydrogen sulfide a pKa of 7. So water is the weaker acid, and our equilibrium will always lie on the side of the weaker acid and the weaker base. And again, we see the same trend within the hydrogen halides as we move down the periodic table from fluoride, from HF to HCl to HBr to HI. Our acidity will increase, and our pKa values will decrease. The stronger acid has the smaller pKa.